Hi all. Let's we discussed in the previous lecture about P and complexity of algorithms, what this means in general, and so. But I couldn't really assign homeworks on that, so I gave a couple of homeworks where you can feel or see how the difference in numbers is affected by the type of growth rate. And so number 20, that was the first one I assigned. There, what you did is you have different type of growth rates, and the question is, what happens if you double your input? Because that's very often what you might say. Okay, say from you will. Typically, what also happens is when algorithms get faster, let's say cracking cryptography, which we're going to talk about much later, or in much more detail, but. What was impossible to crack 10 years ago because the computers were not fast enough, unless you had a supercomputer or something like that, or you put a lot of effort in there, it's now can be routinely calculated because, well, our processors are much faster. And what one often does is said, okay, we used to use prime numbers, we'll see later why prime numbers, of, let's say, 7 digits, but now we have to double digits, so we make it 14 digits, and so we get this kind of doubling. It's of course you could just say we make it one more digit. That's what was another question in the homeworks, but here we talk about doubling, which, well, let's see the effect of that. So the first one was the log n. So if we had an algorithm with this complexity, what is the result of that? So what we needed to do was just plug in log of 2n and compare. What is how do these two compare? So the question is, how do they compare these two values? Okay, this is the, let's say, the old value, and this is the new value. Now these are, you remember, log is so it really means that you take the logarithm of the logarithm. So let's take the logarithm inside. Now we know this is the nice rule, is that logarithms of a product, they become sums. If you don't remember this anymore, go look at your early textbooks on college algebra and so on logarithms. Now the log of 2, but since this is base 2, is just 1. Remember, the log is the exponent you need to write 2 as a power to that exponent. So, sorry, yes, sorry, I say it again. The log of a number, like say the log of 5, is 2 to the what power do I have to write? That is, the log of 5 is the number that you need to make 5 equal to a power of 2. And so, of course, in the case of log of 2, that's just 1. So this is this number is 1. So now we have to take the log of log n plus 1. Now, there's no formula for that anymore. Be very careful. Some of you might have come up with a clever formula, but it doesn't exist. So there is no formula that says what is the log of a plus b. But to have an idea, I'm going to be very, very crude here and say, okay, that is at most the log of n plus 1 more. And it's way, way smaller. If you can try with numbers. So, sorry. Let me say what I mean. Let me say it here, and then I'll apply it. What I'm trying to say is that if you take the log, I said there's no formula for that, but what you could say is, for instance, the log of a plus 1 is less than the log of a plus 1. So you cannot write an equality anymore, but you can mark an inequality. Now, this is really, really, really a very bad approximation. For instance, if a would be, say, 15, now the log 2 of 15, or like 16, let's take 16, let me count. Log 2 of 16 is 4. Okay, now what is the log 2 of 17? Okay, I'll do it for you in my calculator. I do this. I'm not showing it how I do this. I hope everybody knows how to calculate. Yeah, you're right. Yes, while I'm saying this, oh no, my calculator has a log 2. Some calculators might not have that, so that is a bit of a nuisance, of course. But then you have to use convert it to a natural logarithm. So this is 4.08. So in other words, and I'm claiming it's less than 5. That's clearly the case, right? So if I apply this here, then I get that the log of this is 1, right? So let me write up what I have here. This is log of n plus 1. Okay, I'm rewriting just what I had because I said this was 1. Okay, now what I'm using here is that I can replace, I can put the plus 1 out, but it just is not equal anymore, it's just smaller. This is the log of the quantity that I had, which was log n plus 1. So what I'm trying to say here is doubling the input makes at most one more step, but it is at way much less if you see it like that. Okay, but okay, this is a small number, but it actually doesn't matter. The smaller, the bigger this number is, the smaller the difference is going to be. Weird, but that's how it works. But okay, nonetheless. So the question was a little bit vague in what it actually really wanted. So I'm interpreting the question as being answered by saying this. But some of the, so if it's log of n, so we have to now compare log of n of the log of, replace n by 2n, and there it is really equal to, now we have really equal. It's one more step. Okay, doubling the input in a algorithm of complexity log n is just one more step, which is almost nothing, right? Now let's look at the next one would be a linear algorithm. They say 100n here. I have no idea why the 100 comes from. Just to show you that the 100 doesn't really make much of a play. Let's see. That is the original. What is the new one? That would be 100 times 2. That's 200n. Well, what it does is just doubles, right? So here we have double the number of steps. The 100 you see doesn't really do anything. Even if there would be no 100, n becomes 2n. So you basically double the number of steps, which can be already right. If something takes 5 minutes, it would now take 10 minutes. Okay, but these are reasonable things, right? That's why linear algorithms are not considered really considered rather good. But let's look at the next one. N log n. This is a complexity that we will see much more, especially when we do discrete math 2. For instance, there are sorting algorithms that are of this time. Ours that we have seen so far is n square, but this is n log n. Let's see what the result of that is. So now remember, what I always do, I hope what you understand what I'm doing. I'm replacing n now by 2n. So this would be 2n log 2n. So let's see what this is. This is 2n. Now the log is the same what we did up there. That is the log n plus the log of 2, which is 1. Okay, I'm just doing this in one step. So what is so if I work this out, it's 2n log n plus 2n. Okay, and so what is the difference is, well, first of all, we have to double. It will be twice as long plus 2n. Okay, so if the previous one took 5 minutes, this will now twice as long. This part here, right? That is 10 minutes, but it also depends on how big n is. The bigger n is, the worse this is going to become. Okay, so it is worse than doubling, because the doubling happens here. This is worse than doubling, but for instance, the next one is, I think, n square, right? N square. What is happening here? If I double the input to n square, 2n squared. Sorry, it's the n replacing by 2n, so the 2 will also be squared, so that is 4n squared. So this becomes 4 times the number of steps. Okay, which is not that dramatic. 4 times the number of steps, 5 minutes becomes now 20 minutes. Okay, so right. Okay. Notice that is in some sense also, okay, 2n, in the previous one, 2n is smaller than 2n log n, right? So we could even have made this less than 2n log n, and we could replace this by the bigger number 2n log n, and this whole thing would be 4n log n, so it would also be 4 times. So this is, sorry, this is not supposed to be, I don't know what this came out so weird, but I meant to say this is 4 times the number of steps. So this is better than 4 times the number of steps. If you would replace this 2n by 2n log n, a bigger quantity, then it's the same. Then it will also be 4 times the number of steps. But this is smaller. So it is a bit less than 4 times the number of steps. it's not right to say it's 3 times the number of steps, but it is somewhere in between there. And then, of course, things get really bad when we take higher power, so n cube. Then there becomes 2n cube. You see it's now 8n cube, so it's 8 times as bad. But you see, this is why polynomial is not such a huge thing. Just doubling, okay, the higher the power, the higher the degree of the polynomial is, it's not, if we are the double input, then I have to, in the n square quadruple, in the n4 part, I don't know how you call that, octodouble or something like that, 8 times as much you have to do, but it is still within control, right? So if you have an algorithm that is polynomial time, but you don't know exactly, is it now degree 5 or degree 4? This is like, we don't know exactly. We know it's something degree 5, but we perhaps can do degree 4. It means that if you would double the input, worst case scenario, it's degree 5, then would be 2 to the, what would that be? 2 to the 5, 32 times more time, which is still something you might consider. You say, okay, this is an important problem. If I can crack this with my laptop in 10 minutes, but if I have to double the input, then it's going to take 10 times as much, 320 minutes. Okay, 5 hours. What I do is I'll go to sleep, put my laptop to work, go to sleep, and in the morning I will have it. See, this is important that we kind of can predict how long something will take, right? So it's also that we can like assign a particular computer to do this task because we know it will take him this long. Okay, and so finally, I think it was the exponential time. So now you see how much dramatic is exponential time. So we have 2 to the n. Make sure that this is 20. I keep looking at the wrong one. No, I got the right one. 2 to the n. So this would now be 2 to the 2n. Now, what is that? Well, it's perhaps harder to come up with a formula unless you remember a little bit about powers of powers of powers. A power of a power is multiplying the exponent. So what it does, this says it is square of the original. So we have to square the amount of time. So if the previous one took this many steps, this one is going to be the square of the number of steps. Okay. Now that is, we have to be a bit careful here because squaring is a process where the units are important, right? If you say, okay, square 1 minute, that's 1 minute square. What does that mean? 1 minute square, right? Because okay, if you just square 1 minute, 1 squared is 1 minute. That's clearly not the case, because if you take 60 seconds and you square that, that is 3,600 seconds, which is an hour. So when you do these manipulations, when you transform the number of steps in the number of times, one have to be a little bit careful. Okay, so I have explained in a video that there's a difference between the number of steps and the time it takes to carry something out, because it depends on the processor, the speed of the processor. In fact, there were homework problems like that too that I assigned, I think one of them at least. I hope that was okay too. But okay, let's move on. It's not important. It's just to give you an idea how things are. So, in other words, for instance, in the case of G, let's say, if I had to do something and it took about 1 million steps to carry out, which is not much for a modern day computer, because we've seen there we regularly we think of these things to be able to carry out 10 to the minus 11 or 10 to the minus 9, which is, and 1 million is 10 to the minus 6. But if I have to square this, so think about it, 10 to the, we can do 10 to the 6, 10 to the 9 calculations with a regular computer. Say I forget now exactly what is this, what we say in the modern day computers. I think 10 to the 9 is considered to be kind of what normal computer can do. 10 to the 9 calculations in 1 minute. Okay, so this and let's say just 1 minute. Now we have doubled. This is how, let's for simplicity say we have a problem that it takes exactly 1 minute to calculate. That means this is the number of steps it will needs to do. Now remember, if I, in case G, I have to square this. The number of steps will now be the square of the previous number of steps. So let's look what that means. That's 10 to the 18 steps. What is that? That is 10 to the 9 times 10 to the 9. Perhaps a better way to say that. Now, 10 to the 9 steps can be done in 1 minute. So how many minutes does this one take? Well, it takes 10 to the 9 minutes. Now, that is a big number, people. That is a huge number. This is what is this? 1 billion. 1 billion minutes. I'm not going to say it's the age of the universe, but let's see, how much would that be? And a day is about 10,000 minutes. A year, therefore, is about 4 million minutes. We are talking about something that will therefore take about 25 years, give or take. Just by doubling it. That's amazing, right? Just by doubling the input, what could be carried out in 1 minute with this particular processor, which can carry out, I'm assuming we have a processor that can do 10 to the 9 bit operations in 1 minute. If I double the input, it will, instead of 1 minute, take about 25 years. That is an enormous change. And that is why exponential time is such a bad thing if you want to try to carry out the algorithm, and therefore it's so good if you want to use it to protect your to encrypt your data. And we haven't talked about cryptography in detail yet, but I hope you have some idea. I've explained a bit in the text how it works, right? So that's the effect of it. Okay, let's move on very quickly. This one doesn't take us much time. We spent a little bit trying to explain this. It is good to see a little bit, to have the feel for what these things are. Okay, 39. So we have two algorithms, linear search and binary search. Okay, now let's remind you how that linear search works. So linear search had a complexity of O n. Simply because you basically go through the whole list until you find the element you're looking for. Now, binary search had a much better complexity, and that complexity was O of log of n. Now, granted, for binary search, you had to have an ordered list, which for linear search you did not. But let's assume that we are lucky and we had an ordered list. You could still do linear search on it, right? You still keep looking at it. It kind of seems... Why not? In fact, that is if it's up to us. If you let's say, oh, okay, you're in a store and you have to find your size, and there's on the rack and it's like the numbers size. I'm gonna make up sizes because I don't want to put anybody on the spot. Size 7, size 8, 9, 8.5, 9, 9.5, so and so on. Well, you kind of go through the whole thing until you find what you want. So we, even if it's ordered somehow, we still will kind of browse through it that way. The same way with as I said, very often when it's small things, we do linear search even if it's ordered. But okay, is there a difference? So the question is now, again, same problem. What if the size of the list, so L was the size of the list, what if we make it twice as long? Okay, so in linear search, this becomes now O2n. Okay, so that means basically, well, the complexity is the same, but the question was not about the complexity. Sorry, I wrote complexity, but I should have said the number of steps. I don't remember anymore exactly what our formula was, but we have now seen if it was, so this means that it is grows, we can think of this as the same growth of magnitude as n, although there might be a constant, it might actually be 5n, but it doesn't matter, right? Because if the original was n, this is the original, okay? And now this is the original list, and so here's the new list. That would be now 2n steps, because the new list also has now twice as many. So it would be twice as many operations, twice as many steps. Sorry. This is for linear search. What about binary search? Well, the original was log n, and the new one is now log of 2n, which we have seen before. That is now 1 plus log n, right? Remember, it's because it's base 2. So in other words, is one extra step. Which is basically nothing, right? One extra step, what is that? If we are talking about big lists like a million, billion perhaps, like database, big huge databases, big data, right? And twice as many steps, okay, that's more steps. That's kind of, you know, if we're talking about a billion, that could take twice as much time. We have discussed this before with the previous example. But with a list twice as big, no biggie. Just one extra step. Remember, why is it? Because binary search just cuts everything in two and just, okay, says it's only one piece that I have to look at. I cut it in two. Which piece I look at? Okay, that's the piece. And forget about the other piece. So you have doubled it, and after one step, it already knows in which part that it's in of your doubled list, so to speak, where it is now located, element it's looking for. Okay, that is it.